Just remember the final exam is on Wednesday, almost the end of the final exam period, December 21st. Not at 9 o'clock, but exams at Lehman start at 8:30 in the morning. And so you have to be up bright and early. And the best review is always homework problems. So if you recall the review for the midterm exam, it was just a list of problems in the book. Essentially just another set of homework problems, but no different at all from the homework problems you had been assigned. And the final exam has two parts, basically. It's the chapters covered in the first part of the course. So the introductory chapter 1, chapter 2, and chapter 5, and what we've done since the midterm, chapter 7 and chapter 8. So that's what the final exam covers. And I think I'll spend today going over some problems from chapter 7 on series solutions. And I'll spend Monday going over problems from chapter 8 on the Laplace transform. And if you have questions about anything else, I am very happy to go over them as well. Okay. Any questions about any of that?
Professor, I thought the final exam was on December 19th.
I think I follow exactly the CUNY final exam schedule. And I have a class that meets after this where the exam is the 19th, but right now I will double check the final exam schedule and make sure, all right? But we do whatever Lehman says we are supposed to do. So let me see if I can find the final exam schedule. It would be great if it were on my computer somewhere. Let me just see if I can find it.
Remember, sir,
I'm sorry, I didn't hear what you said. Okay. So we're interested in power series and power series solutions of differential equations. A power series, which you should have learned a little bit about in Math 176 and Calc 2, second semester calculus. It's an infinite series that looks like this. We think of this as a series which converges on some interval, because if you let x equal x naught, this is just 0. So suppose this series converges, and we call this a function f of x. So f of x naught would be summation n goes from 0 to infinity, an x minus x naught to the n. What does this mean if you start to write down the first few terms? When n is 0, you get a0, x minus x naught to the 0, which is just 1. So a0. Plus a1, x minus x naught to the first power, plus a2, x minus x naught squared, plus a3, x minus x naught cubed, and so on forever. This is the sum of infinitely many terms. And if you let x equal to x naught, if you evaluate this at x naught, you get a0. And when x is equal to x naught, all of these other terms are 0. So f of x naught is a naught. So this function is always defined at x naught. And what will always happen is that there will be some interval whose center is at x naught, and this power series converges in this interval. So this is an interval from, say, this is, say, x naught plus r, and this is x naught minus r. So f of x converges always in an interval centered at x naught of the form x naught minus r, x naught plus r. And you can also have that r is infinity. That means the series converges for all x. So a power series always converges in some interval around its center. And the largest r that satisfies this convergence criterion is called the radius of convergence of the series. And it could be infinite. You can have a series that converges for all x. So the simplest examples and the classical examples are, suppose you have an equal to 1 for all n. So f of x is the series summation x minus x naught to the n goes from 0 to infinity. And the way you understand the convergence of a power series is always as the limit of the partial sums. So if you have the series f of x equal to summation n goes from 0 to infinity, an x minus x naught to the n, what is called the nth partial sum of the series, we call it, right, this is a capital N, is just the sum. N goes from 0 up to, let's say, n minus 1, an x minus x naught to the n. And the series converges if the limit of this, as n goes to infinity, exists. So this, again, is what you were supposed to have seen in Calc 1. And if you take, let's say, really the simplest case, suppose you take x naught equals 0. So your series is summation an x to the n goes from 0 to infinity. And the simplest such series might be the case when an equals 1 for all n. So you have summation n goes from 0 to infinity, just x to the n. And what is the nth partial sum? It's summation x to the n n goes from 0 to capital N minus 1. That's 1 plus x squared up to x to the n minus 1. And this is a series which is a geometric progression. And we can evaluate this explicitly. This is 1 minus x to the n over 1 minus x, where x different from 1. And so this makes sense if x is less than 1 in absolute value. If x is less than 1, this converges. And if the absolute value of x is less than 1, then x to the n goes to 0 as n goes to infinity. So summation x to the n, this infinite series, is the limit as n goes to infinity, 1 minus x to the n over 1 minus x. This is 1 over 1 minus x if absolute value of x is less than 1, and the series diverges, doesn't converge, if the absolute value of x is greater than or equal to 1. So this very simple series has the property that it converges on the open interval from 1 to minus 1. So summation x to the n goes from 0 to infinity, has radius of convergence r equal to 1. And in that, on this interval, this f of x is just equal to 1 over 1 minus x. There are two basic examples of power series you have to know. This is the first, the geometric series. And the second is the series f of x equals summation 1 over n factorial x to the n. N goes from 0 to infinity. And this series has radius of convergence infinity. This converges for all x, and this is just the exponential function e to the x. So this is one of the most important facts in mathematics and everywhere, including in the case of differential equations, and we use it all the time. Now, one nice property of a power series, so suppose your power series converges, the derivative you get just of the function is just obtained by differentiating each term all by itself. So the derivative of an x to the n is n a sub n x to the n minus 1. Of course, when n is 0, this just gives 0. So I could write this as summation n going from 1 to infinity, an x to the n minus 1. Or if you prefer n to be the power of x, here as n goes from 1 to infinity, n minus 1 goes from 0 to infinity, but the coefficient an, the n is 1 greater than the exponent, so this would be an plus 1. So that would be another expression for the derivative. And this is a power series with the same radius of convergence, so you can differentiate it, and you differentiate again term by term. So this is the derivative of f prime of x. That's the derivative of, what's f prime of x? Summation n an x to the n minus 1. You differentiate term by term, you get n minus 1 an x to the n minus 2. All right? So that's the formula for the second derivative. And again, when n is 0, this is 0. When n is 1, this is 0. So this term really starts with 2. Or if you just want to shift the index, so I'm looking at just powers of x to the power n. If you replace n by n plus 2, you get n plus 2, n plus 1. A sub n plus 2 x to the n, and goes from 0 to infinity. So So these are some of the basic facts about power series. And if you just analyze this a little bit more carefully, you find a very nice fact that relates the coefficients, a sub n, x to the n goes from 0 to infinity, to the derivatives, this an, which is called the nth Taylor coefficient. So power series is sometimes called a Taylor series. An is exactly the nth derivative of the function f evaluated at 0 divided by n factorial. So these are all useful facts that we talked about when we were looking at power series. And we use power series to solve differential equations that are too hard to solve explicitly.
Professor, can you move the page?
Yep.
Thank you.
So suppose we have a second order differential equation. Well, I'll write it like this: P0 of x, y double prime, plus P1 of x, y prime, plus P0 of x, y. Let's say it's homogeneous equals 0. So this is P0, and this is, sorry, call this P2. Yeah. Where P0, P1, and P2 are polynomials. And we like differential equations where the coefficient of the highest derivative is 1. So we would like to divide by P0 of x. If we can do that, we get y double prime plus P1 of x divided by P0 of x, y prime, plus P2 of x divided by P0 of x, y equals 0. But of course, you only can divide by something that's non-zero. So if you can divide if P0 of x is not equal to 0 in some interval. And so that's the simplest case, when you can just divide by P0 of x. And now these functions are some rational functions, and say P0 at naught is different from 0. So so we have something that looks like now the coefficient of the second derivative is just 1, y double prime I'll just leave it like this. This is our differential equation. And so what we're looking at are differential equations of the form P0 of x, y double prime, plus P1 of x, y prime, plus P2 of x, y equals 0. So this is a second order, because the highest derivative is the second derivative, linear ordinary differential equation with, let's say, P0, this, and P0, P1, and P2 are polynomials. That makes things a lot easier. If these were complicated functions, arctangents of exponentials and so forth, you couldn't use this method very easily. But for polynomials, things are more straightforward. And P naught of 0 is different from 0. So we can look for a series solution, an infinite series solution of this differential equation around x naught. More generally, if P naught of x naught were different from 0, then we look for a solution of the form y equals summation an x minus x naught to the n. An infinite series solution centered around x naught. And in a beginning course in differential equations, I want to make things as easy as possible. So we're really just going to consider the case when x naught is 0. So we're going to look for a solution of a simple infinite series. N goes from 0 to infinity. This is just an x to the n. So the best way to do this is an example. And I'll pick one of the homework problems that in section 7.2, I had assigned problems 1 to 8. So let's do one of them. Maybe I'll pick on page 329. Exercise 2. So let me start with a fresh piece of paper. So this is page 329. Exercise 2. We have the differential equation 1 plus x squared y double prime plus 2xy prime minus 2y equals 0. So this is of the form p0 of x y double prime plus p1 of x y prime plus p2 of x y equals 0, where the coefficient y of the second derivative is 1 plus x squared. So p naught of x in this problem is 1 plus x squared. The coefficient of y prime is 2x. So p1 of x is equal to 2x. The coefficient of y is minus 2. So p2 of x is minus 2. So this is a differential equation, second order linear, homogeneous, the right-hand side is 0, with polynomial coefficients. And we want to find a power series solution. Around x naught equal to 0. And notice p naught of 0 is 1 plus 0 squared, which is 1 is not 0. So the coefficient of y double prime is not 0. So let's just do it in sort of brute force fashion. Suppose we let y be summation an x to the n. N goes from 0 to infinity. So y prime is summation n goes from 0 to infinity, and an x to the n minus 1, which is also summation. If I replace n by n plus 1, I get n plus 1, an plus 1, x to the n goes from 0 to infinity. So here's the power of x, it's x to the n. And the second derivative is summation n goes from 0 to infinity, n minus 1, a sub n, x to the n minus 2. And if I replace n by n plus 2, I get n plus 2, n plus 1, an plus 2, x to the n goes from 0 to infinity. And now I want to take these series and plug them into the differential equation and try to compute the coefficients a sub n. That is, so we have 1 plus x squared y double prime plus 2xy prime minus 2y. That's all going to equal 0. Let's see, what is this? This is y double prime plus x squared y double prime plus 2xy prime minus 2y. And let me plug in the series that I just calculated. So y double prime is summation, n goes from 0 to infinity, n plus 2, n plus 1, a n plus 2, x to the n. X squared y double prime. Let me keep my y double prime in this form, because now if I multiply it by x squared, x to the n minus 2 times x squared is x to the n. So x squared y double prime is summation. I'm using this formula. N goes from 0 to infinity, n minus 1 a n x to the n. And I have 2xy prime. Here's y prime. If I multiply this by x, x to the n minus 1 times x is x to the n. So I get plus summation, n goes from 0 to infinity, 2 xy prime. That's 2n a n x to the n. And minus 2y, that's just minus summation, n goes from 0 to infinity, minus 2, well, minus 2 an x to the n. So I have 4 series here, and I collect the terms. This is summation, n goes from 0 to infinity. I have something times x to the n. What do I have? I have n plus 2, n plus 1, an plus 2, plus n, well, I'll do this, n minus 1, an, plus 2n an, minus 2an. Let's see, what is that? That's summation, n goes from 0 to infinity, n plus 2, n plus 1, an plus 2, and I have something times an. This is, let me factor out the an. This is an times n squared minus n plus 2n minus 2. So that's n squared plus n minus 2 times a sub n. That's the coefficient of x to the n. And for this to be equal to 0, the power series is equal to 0 only if all of the coefficients are equal to 0. So the coefficients, so let's just remember, we have the solution y equals summation an x to the n equals 0 to infinity. That's the solution of the differential equation. But we have to know what the an are, so we must compute the an's. And what we see from this relation is the power series is 0, identically 0. That only happens when every coefficient is 0. So the coefficients have to satisfy this plus this is equal to 0 for all n. So in our power series, we have summation, y is summation an x to the n. And these coefficients satisfy the recursion n plus 2, n plus 1, an plus 2. plus n squared plus n minus 2 times an equals 0 for all n. Let's see, n squared plus n minus 2, I think that factors, right? I think this factors into n plus 2 times n minus 1. So n plus 2, n plus 1, an plus 2, plus n plus 2, n minus 1, an, that equals 0 for all n. And I can cancel the n plus 2, so I have the relation n plus 1, an plus 2, plus n minus 1, an equals 0. So given some values for a0 and a1, we have that an plus 2 is equal to minus n minus 1 over n plus 1 a sub n. Let's see, let's calculate some of these numbers. So a2, if we let n equal to 0, we get a2 is minus 1 over 1 a0, which is a0. If we let n equal to 2, we get a4 is, see, when n is 2, it's minus 1 over 3 a2, and a2 equals a0, so that's minus 1 over 3 a0. If we let n equal to 4, we get a6 is equal to, so let n equal to 4, I get minus 3 over 5 a4, which is minus 3 over 5. And what is a4? a4 is minus 1/3 a0. The minuses cancel and the 3's cancel. This is 1/5 a2. That's nice. Let's do a few more and let's see if we see a pattern. If we let n equals 6, we get a8 is equal to minus, when n is 6, this is 5 over 7, a6, which is minus 5 over 7, and a6 was 1 over 5, a0, so we get minus 1/7 a0. Let's do another couple, n equals 8. So a10 is equal to minus, see, when n is equal to 8, this is 7 over 9 a8. That's minus 7 over 9 minus 1 over 7 a0. The minuses cancel, the 7's cancel, we get plus a 9th a0. So we should recognize a pattern here. When we calculated in our series y equals summation an x to the n, looking at the even coefficients, we found a0 is a0, a2 is minus 1/3 a0, a4 is plus 1/5 a0, a6 is minus 7 a0, a8 is plus 1/9 a0. If you look at this, we have a0. First of all, the signs are alternating, plus, minus, plus, minus, plus, minus. And second, the numbers in absolute value are just the unit fractions with odd denominators. 1 over 1, 1 over 3, 1 over 5, 1 over 7. We might guess that in general, a sub 2n, right, take an even exponent, will be plus or minus 1. Let's see. it's minus at 2 times 1, 2 times 3, and so forth. Might be minus 1 to the n, 1 over 2n plus 1 times a naught. Because again, if you let n equal to 0, you get a naught. If you let n equal to 1, you get minus a third. So this is like my guess. And we know this is true. We just checked it for n equal to 0, 1, 2, 3, and 4. Suppose this is true for some n. So assume this is true for some n. What about the next even number? The next even number is a sub 2n plus 2, which is a sub 2 times n plus 1. If we go back to our recursion, let me write that down again because it's very useful. The recursion formula was an plus 2 is minus n minus 1 over n plus 1 times an for all n. Actually, I don't even need this part. An plus 2. So if I replace n by 2n, I get minus 2n minus 1 over 2n plus 1 times a sub 2n. And a sub 2n is this. So this is minus 2n minus 1 over 2n plus 1 minus 1 to the n over, oops. Let's see. A sub 2n plus 2. Yeah, sorry. A sub 2n plus 2. So this is 2n minus 1 over 2n plus 1. Let's see. Let me make sure I get this recursion right. So an plus 2 is minus n minus 1 over a plus 1 a sub n. So if I let n be equal to 2n, this is 2n minus 1 over 2n or a sub 2n. A sub 2n is minus 1 to the n, 1 over two n plus 1 a naught. Oh, wait a minute. Sorry. My guess was this is 1 over a sub 2n. So, yeah. So we have a2 is a naught. Sorry. I copied these down wrong. So a2 is a naught. A4 is minus a third. A6 is a fifth. A8 is minus a seventh. A10 is a ninth. So that recursion is this is 1 over 2n minus 1. And now everything works out because these cancel. And I get minus 1 to the n times n times minus 1 to the n is minus 1 to the n plus 1 over 2n plus 1 a naught. So I've worked out explicitly all of the even coefficients of my power series. And now let me try to work out the odd coefficients. So again, I have my power series solution. Y is summation an x to the n. N goes from 0 to infinity. And these coefficients satisfy the recursion relation. An plus 2 is minus n minus 1 over n plus 1, a sub n. Let me do this again. Let me try and do it as carefully as I can. So given A1, what is A3? So if I use this formula with n equal to 1, I get A3 is minus one minus 1 over 1 plus 1, A1, but 1 minus 1 is 0. A3 is 0. A5, if I use this formula with n equal to 3, but if A3 is 0, then A5 is something minus, so n is equal to 3. 3 minus 1 is 2, 3 plus 1 is 4. A3, but A3 is 0. This is equal to 0. And in fact, what this says is, if A3 is 0, then A5 is 0. If A5 is 0, A7 is 0. In fact, AN equals 0 for all odd numbers n greater than or equal to 3. This recursion tells us that the odd numbers, the odd coefficients, except for n equal 1, are 0. So if we have y is summation, n goes from 0 to infinity, a sub n x to the n, we have the even coefficients, n goes from 0 to infinity, a sub 2n x to the 2n, plus the odd coefficients, the odd powers of x. But the only odd power of x, which does not have a coefficient of 0, is the first power, plus a1x. So y is a series that looks just like this. And again, let me just, because this is really very important, and I want to make sure I do this correctly. Let me compute the even powers of this power series. So here is my recursion. So A0 equals A0, of course. A2 is equal to, and so this is this formula with n equal to 0. I get minus 1 over 1. A0 is A0. So A0, O2 is A0. A4 is minus, using this formula with n equal to 2, minus 1 over 3 A2, which is minus 1 over 3 A0. A6, I'll do it over here so we can see. A6, so when n equals 4, this is minus 3 over 5 A4, which is minus 3 over 5 minus 1 over 3 A0. So A6 is plus 1/5 A0. And again, we will get the recursion formula that A sub, let me use the letter M, A sub 2M is going to be equal to a certain power of -1, which will oscillate back and forth, 1 over 2m minus 1 a0, and if this is no, when m is equal to 2, this is odd. So a6, when m is equal to 3, this is plus 1 over a fifth. So this is my a sub 2m. So if I plug this into the series, the solution to this whole problem is y equals summation, say m goes from 0 to infinity, a naught minus 1 to the m minus 1 over 2m minus 1 x to the 2m plus a1x. And that's the answer. All right, so so this is the basic problem for solving a differential equation in power series. In the case when the coefficient of your y double prime is not 0 at 0. We have what's called an ordinary point and not a singular point. Okay. So this is a technique that you have to master, and you have to make sure you master it before the exam, because it takes a lot of work to do these problems, and if you know the method, then you can do it fairly quickly. Otherwise, it takes forever and you make mistakes. And the second case of using series solutions is when you have what is called a regular singular point. And when you have a regular singular point, you have a differential equation that looks like this. Let me just make x naught equal to 0. So we have an equation that looks like x squared a of x y double prime plus x b of x y prime plus c of x y equals 0. And a, b, and c are polynomials. And so x squared a of x is a polynomial, but this is 0 at 0. So you can't just divide by this around 0. And I want these to be polynomials where a at 0 is equal to 0, is not equal to 0. So x squared a of x is a polynomial, and x is a root of that polynomial of what we say order 2. So x squared a of x, a of 0 is not 0. So this is a very special kind of polynomial. B of x and c of x are arbitrary polynomials. And in the simplest case, which is all we're going to look at, a of x is a number a, b of x is a number b, and c of x is a number c. So we're just going to look at equations that look like a x squared y double prime plus b x y prime plus cy equals 0, where this is non-zero, so we really have a second derivative there. Right. And we had a method to solve this kind of equation. If you divide by x squared, you would get ay double prime plus b over xy prime plus c over x squared y equals 0. And we look for a solution of the form y equals just a power of x. Y equals x to the r. Of course, if y is x to the r, y prime is r x to the r minus 1, and y double prime is r minus 1 x to the r minus 2. So if we take these expressions, these polynomials, and plug them into the differential equation, we get ay double prime is r minus 1 x to the r minus 2 plus b over x y prime. If you divide this by x, you get x to the r minus 2. So we get br x to the r minus 2. And if you take y and divide it by x squared, you get c x to the r minus 2. And that has to equal 0. Oops, I'm sorry, I said this backwards. I didn't say it backwards, but everything I said was correct. But let's just make it easier. So let me just go back to this equation. We have a differential equation ax squared y double prime plus bxy prime plus cy equals 0, where a, b, and c are numbers, real numbers, and a is not 0. And we look for a solution y, which is the power of x. So y prime is rx to the r minus 1, and y double prime is r minus 1 x to the r minus 2. So I take these expressions and I plug them into the equation. So x squared times y double prime, I get a r minus 1. And if I multiply this by x squared, I get x to the r. Plus b xy prime, so I have r, x to the r minus 1 times x is x to the r, and cy plus c x to the r. I can factor out the x to the r, that's a, r minus 1 plus br plus c, x to the r equals 0. And if that's going to be equal 0 for all x in some region, then this coefficient has to be 0. So a r times r minus 1 plus br plus c equals 0. So r is a root of the quadratic equation of that quadratic equation. And if we're lucky, that quadratic equation has two distinct real roots, and we have a solution. So the simplest example, suppose we have x squared y double prime minus xy prime minus 8y equals 0. So the coefficient of x squared, a is 1, b is minus 1, c is minus 8. So this equation, this quadratic equation becomes a, which is 1, r times r minus 1, plus br minus r minus 8 equals 0. That's r squared minus r minus 2r minus 8 is 0. And this factors. This is r minus 4 times r plus 2 equals 0. So r is equal to 4 or minus 2. So this differential equation has two solutions, y equals x to the 4th and y equals x to the minus 2, or 1 over x squared. And then any linear combination of these will be a solution. So that is the simplest case. And the more complicated cases are when this quadratic has either a double root or no real root. And what happens in that case is the following. So we have a x squared y double prime plus bxy prime plus cy equals 0. And we look at the quadratic ar times r minus 1 plus br plus c equals 0. And there are three cases. In the first case, we have two real roots, two distinct real roots, r1 and r2. So x to the r1 is a solution and x to the r2 is a solution. And so any linear combination of them is a solution, and every solution is of this form. That's when we have two distinct real roots. In the second case, we have a double root. For example, and so there's only one real root of this equation, and in such a sense it occurs twice. You have a double root r1, so x to the r1 is one solution, and log x to the r2 is a solution. And so any linear combination of them is a solution. And in the third case, we have two conjugate complex roots. So there are no real roots. The complex roots are r1 and r2 equal to lambda plus or minus I omega, where omega is not 0. And in that case, we have one solution is x to the lambda times cosine of omega log x, and x to the lambda sine of omega log x. So this is a little more complicated. And any linear combination of these is a solution. So those are the three cases, and that tells you how to solve every differential equation with a regular singular point of this form. So let me just do one or two examples. Yeah,
The previous page, can you show the bottom?
sorry, show what?
Can you show the bottom of the previous page?
Yeah, sure. But again, this is everything is in the book and legible. So this is theorem 7.4.4.3 on page 345. So that's where you find all this stuff. So let me just pick a couple of problems at the end of this section. I'll just pick some at random, say number 7. We have x squared y double prime plus 3xy prime minus 3y equals 0. So the coefficient of x squared is a equal 1. The coefficient of x is b equal 3. Coefficient of y is c equal to -3. And we always look at the quadratic equation r minus 1 plus br plus c equals 0. So in this case, the equation becomes 1 times r minus 1 plus 3r minus 3 equals 0. This is r squared minus r plus 3r plus 2r minus 3 is 0. Let's see, this I believe can factor into r plus 3 times r minus 1 equals 0. So we have two distinct roots, minus 3 and plus 1. So the general solution is C1 x to the minus 3 plus C2 x to the plus 1. That's the solution, the general solution of this differential equation. And let's just check. So if this is y prime is minus 3c1 x to the minus 4 plus c2, and y double prime, if I differentiate this again, I get 12c1 x to the minus 5. So x squared y double prime C1 x to the minus 5 plus 3x y prime minus 3 C1 x to the minus 4 plus C2 minus 3 times y C1 x to the minus 3 plus C2x. Let's see what we get. We get 12C1 x to the minus 3 minus 9C1 x to the minus 3 plus 3C2x minus 3C1 x to the minus 3 minus 3C2x. 3C2 minus 3, those cancel. 12 minus 9 minus 3, that's canceled. We get 0. So this checks. Let me do one more. Pick, I don't know, try 18. 2x squared y double prime plus 10x y prime plus 9y equals 0. So A is 2, B is 10, C is 9. So my equation A, it's always A, R minus 1 plus BR plus C equals 0. So that's 2R times R minus 1 plus 10R plus 9 equals 0. This is 2R squared minus 2R plus 10R. That's plus 8R plus 9 is 0. Let's see. I can always use the quadratic formula, or I can try and factor it. Let's see. This might be 2R plus 3 times R plus. Is that right? Well, let's just use the quadratic formula. So R is minus B plus or minus the square root of B squared minus 4AC over 2A. So R is minus 8 plus or minus the square root of 64 minus 72 over 4. That's minus 8 plus or minus the square root of minus 8 over 4, which is minus 8 plus or minus 2 root 2I over 4, or minus 2 plus or minus root 2 over 2I. So if I solve my quadratic equation correctly, minus B plus or minus the square root of B squared minus 4ac over 2a. This is minus 8, so that's 2 root 2I. So I have my roots are r equal to, if I write it as lambda plus I omega, lambda is minus 2, and omega is the square root of 2 over 2. So for this differential equation, the two basic solutions are y equal to e to the minus lambda x, sorry, x to the lambda, x to the minus 2 times the cosine of root 2 over 2 log x. And that's the other solution would be x to the minus 2 times the sine of omega root 2 over 2 log x. That's what it is. All right. Questions about anything having to do with power series? So I had a few problems to the kind of review sheet, but really the homework problems are as good as anything else to use as an indication of what you need to know for the final exam.